Okay, so I really like this qualitative quantitative translation type question. So this one we're saying a sample of ideal gas is thermal in a thermally insulated container with a movable piston is initially in state A. As shown in the graph of pressure P as a function of volume V, the gas is taken from state A to state B by an adiabatic process. The dashed lines represent isotherms. So this whole line is at a constant temperature, this whole line is at a constant temperature. So we move from one isotherm to another. So we're saying in the beginning, let W be the work done on the gas, and Q be the energy transferred to the gas by heating. So we have our standard conventions where W is work on the gas, Q is work done by heating on the gas. And delta U is the change in the internal energy of the gas in this process. So the first thing we want to know is W greater than, less than, or equal to 0? So is the work on the system positive or negative? Are we adding energy via working, or are we taking away energy due to working? So in this case, we're going to say, we can kind of look at our situation. We go from a higher volume to a lower volume, which means that our gas is compressed. And the way to compress a gas is to do work on it, is to have your piston, something has to force it down to change and decrease that volume. So we're saying here, oops, volume, it's like a decrease. So the volume is decreasing, which means work has to be done to compress the gas. And then I went one more. But yeah, so in this case, because the volume decreases, that shows us that work is done on the gas. We have this change in volume. All right, the next one is Q greater than, less than, or equal to 0. This one is not too bad at all. The situation tells us that we're dealing with an adiabatic process. It says A to B is adiabatic, and we know that adiabatic means that the heat is equal to 0. We're changing the amount of energy by only working. So based on our first law of thermodynamics, or not even really that, just based on our definition of adiabatic, this heating term is 0 because of our definition. Is delta U greater than, less than, or equal to 0? Briefly explain your answer. So in this case, this is where we can really start to employ our first law of thermodynamics, this idea that delta U is equal to Q plus W. In this case, we said, well, our Q, our heating term, is equal to 0, which means that really our change in internal energy is dictated by the working term, by how much work is entering our system, how much work is done on it. So we said that we have a positive amount of work done onto our system. So the change in internal energy is also positive. It's also increasing due to the positive work done on the gas. So delta U is positive because work is the term that is telling us how our internal energy is changing. So we have a positive amount of work, therefore a positive change in internal energy. If the temperature of the gas in state A is 200 K, Kelvin, what is the approximate temperature of the gas in state B? So I kind of took a little screenshot so we can reference this graph. But so what we want to do is we can really argue this from our gas law, this idea that PV is equal to nRT. So we can see pretty clearly that, well, also in this situation, N is not changing, R is not changing. So we can pretty much figure out the temperature by doing, or really this ratio of temperatures, by looking at the pressure and the volume. Because we know P, we know V, we know N is not changing, we know R is not changing. So really our temperature is just dictated by this P times V. So we can see at state A, the pressure is going to be 1 atmosphere, or 1 Pascal, 1 times 10 to the 5th pascals, and then the volume is going to be just 1 meters cubed. So then we can also do this for B. I just kind of estimated it, so it was about like 5.8 and about 0.3. Doesn't really matter. It's probably a little bit more than 0.3. Actually, that was a pretty bad estimate, but that's okay. So I had that equal to 1.74. So P times V is equal to nRTA. P times V is equal to nRTB. So now we kind of have this situation where we can set up a ratio. We can say, well, 1 is equal to nRTA and 1.74 is equal to nRTB. So again, just our gas law, and then kind of shuffle things around and say, well, nR is not changing and nR is not changing. So we can kind of equate these two through N times R, our number of moles times our gas constant. So we can set those equal to each other. And then we can just kind of do some cross multiplication, get TB is equal to 1.74 times TA. TB equals 1.74 times 200, that given temperature. So TB is about 348 kelvins. I really missed the mark on the temperature. It's probably more like, I don't know, 0.4 maybe. That's my bad. Or the volume. And then also with the pressure, we're really just doing a ratio, so it doesn't matter that I didn't do times 10 to the 5th, but we'd probably want to. If we were calculating numbers, we'd want to do times 10 to the 5th if we weren't just finding a ratio. All right. Is your numerical result for part B consistent with your explanation for part A, or A3? So A3 was asking, is delta U positive, less than 0, or greater than 0? So did we increase our change in internal energy, or did we decrease our internal energy? And we found here in part B that the temperature went up. We have this increase in temperature, so that's consistent. We said before that the way to change your internal energy is to change your kinetic energy of your particles. That's what our internal energy is made up of, the kinetic energy of these particles. And we also said that the way to change the kinetic energy is to change the temperature of those particles. Or if we change the temperature, we change the kinetic energy. So we saw over here that TB is greater than TA. 348 is greater than 200. So our change in energy is positive. We increased our temperature, which means we had to changing the temperature increased our kinetic energy. And when we increase our kinetic energy, we increase our internal energy. So by having a positive change in temperature, we have a positive change in kinetic energy. By having a positive change in kinetic energy, we have a positive change in internal energy.